Hey everybody, so just wanted to do a quick video. It's starting to get into some design patterns you can use in LabVIEW. So I really wanted to start with a foundational, simple design pattern that is scalable, that works well. And this is going to be the state machine. So if you've ever heard of state machine, and this is not a design pattern unique to LabVIEW, this is used across all languages. Basically, it's a behavior model that allows your code to move from one state to another state. And the way that it transitions, it could be triggered by different, events, or it can use logic that's programmed into it to determine which state to move into. So just as like kind of a little demo, and this is straight off the NI website, they have just this little diagram, right? So this is basically a state map for the simple state machine. So we've got an initialized state that's going to move to a power up state, that's going to move to a check status state. And then based off of different conditions, it can transition to different states, right? So if it gets a bit warm, it can go to passive cooling. And if it's cool enough, it can go back to check status. But if it's cooling too slow, then let's go to active cooling, right? So, and it can just basically continue to transition between different states until, shutdown, right? Once there's the shutdown event, we can move to the shutdown and state machine's done. So we can basically define, our different states, and then we can create either logic or events that are going to transition that state machine through different states. One of the cool things with this is you don't have your code running in like a rote mode, right? Where it has to sequence from this state to this state to this state. It can kind of change states on the fly based off of the logic or the capability that you program into it. So really useful design. One of the foundational design patterns available in LabVIEW. So I wanted to show you basically how we can set up just a simple design pattern. So we're always going to be using a while loop. And then in this while loop, let's add a case structure. So this is going to be, each case in this case structure is going to represent a state of this state machine. Now, the way that we're passing the state information into this case structure can be done different ways. Most commonly, this is through enums. So I can drop like an enum constant, and I can add all my states in here and then basically map those states there. You can also do it with strings. Personally, I prefer enums just because with strings you can run into typo issues, et cetera, et cetera. And especially with enums, I can set this up to be a type def. So if I go in and update my type def to maybe add a new state, it's going to update everywhere through my code to now include that new state in the enum. So I prefer them over strings, but you definitely can use just strings as well. So let's go add a couple states to this enum. Let's add an init state, a read state, close, and shut down. Sweet. So now we need to pass in our initial state, so what we want this state machine to start out in. So I'm going to set it to initialize. So it's always going to go to the initialize state first. I'm going to go here and click to add a case for every value. So now we have all of our states mapped here, and I just need to implement the specific functionality that I want in each state here. So for this example, I'm just going to set up a simple DACMX state machine. On initialize, we are going to create our task. We're going to set our timing, and we're going to start our task. So let's set this up. Sweet. Let's say we want 1000 hertz. Set that. Okay. So just a simple, hey, start measuring voltage on some channel. This is my rate, and then, hey, start the task. So pretty basic. Now we need to tell basically the initialized state how it can move on to the next state. Also, as you know, we're going to need, as we transition into different states, we're going to need this DACMX task passed through different iterations. So simplest way to do this is just shift registers. So we can use shift registers to pass data across multiple iterations of loops. You can also do this with feedback nodes. You can use different, DVRs or variables, or a lot of different ways you can accomplish this. Shift registers is a really simple way to do that. So our initialized case is going to basically create the task, and now I want to create a little bit of logic. So let's say if when I start my task it throws an error, then I want it to go to the close state. Rather than try to read data when I know it's not going to work, I'm going to close the task out. But if there's no error, then I want it to start reading data right away. And I can just pass that state out. So super simple. Let's go to our shutdown state. Let's map this real quick. I don't know why I closed this out. I had it pinned. Okay, so we're just going to do a stop. And we'll do a clear. And so our shutdown is actually going to be what is going to, I'm just going to set this to use default if unwired, because this state is actually going to shut down my loop. So I don't really care what it outputs. I will need to make sure I map all the other states though. And let's use default if unwired. So our shutdown state is going to actually end our state machine. Our close. So this is when in our initialized state, right? If we initialize and we throw an error, we're going to our close state. So for close, we want it to stop the task, clear the task. Let's clear any errors. And then we're going to tell it to go back to the initialized state. So our close is just going to say, hey, when we initialized, for whatever reason, this threw some sort of error, right? Let's close out what was started and basically try to start over again. And we can iterate through, so it'll keep retrying to connect until it's successful or until the loop gets shut down. And I can even add a wait in here, so if for whatever reason it's not iterating incredibly quickly in an error state. So maybe add like a second wait. And I could also add in here, if I wanted to, even like some sort of dialogue that says, hey, check that the DACMX physical channels you selected are correct, or make sure the DAC is actually plugged in and powered on and present, or you could add basically whatever you want. I'm just trying to set this up as simply as possible to demonstrate how we can set this up to iterate through states. But yeah, you can completely define what happens in each state. It can sit in this state in like an idle state that maybe is notifying the users that they need to do something, like, hey, I can't find the DAC or something like that. And then for our read state, we're just gonna set this to read data off our DAC, and we can have it displayed. So there's our data. And then we can also add some additional logic. So let's say if this throws an error, we want to go to the close state. So, it could be for different reasons. We could have like a DAC overflow error or something like that. And if there is no error, we just want to go back to the read. And sorry, I guess I am sampling like 1,000 samples per second in this demo. So let's do single channel, multiple samples. Not that it really matters, but just for demonstration purposes, let's be consistent. So here, if this throws an error when we go to read data, we're going to go close out the task, and then which will therefore move back to the initialized state so we can try to reconnect. Or if there's no error, we're just going to keep going through our read state over and over and over again. And let's set this to read 100 samples. Okay. One other thing I wanted to show. So right now there's not actually a way for us to transition into that shutdown state. So let's create one more little bit of logic in this case. We're going to add one more select here. And we're going to create a button. So on the UI, just going to add a simple shutdown button. And if shutdown is true, then we're gonna ignore whatever was selected based off of error and just move to the shutdown case. So, and then we're gonna wire that there. So now, if you click the shutdown button, this will basically ignore this previous logic and just move to the shutdown state, which will actually end our loop. And we can add additional checks, right? So there's no reason your logic has to be as simple as just, hey, if there's an error, close or read. You can add as complex of logic as you want in any case to determine, hey, what to do. So this right here is just a really simple DACMX state machine, but basically it will handle errors on its own, right? So as the DAC task is running, if there's an error in starting up, it's going to close out the task and then try to start back up again. But likewise, when I'm reading data, if there's an error, it can go to a closed state and then it can restart itself back up and then go back to reading. So if for whatever reason I allowed the DAC buffer to overflow or something happened, it can resolve its own issues, which is awesome. So that's some of the real power of the state machine, is we can basically create logic that allows this to become basically define its own behavior, how this code works, and it can transition itself between different states in different sequences based off of the logic that you provide it, which is really powerful. So that's pretty much the state machine design pattern. There's some a little bit more advanced design patterns built on top of state machine. For example, the JKI state machine takes this same basic format and applies some additional tools on top of it that allow it to become even more scalable, a little more organized, stuff like that. And I'll cover that in a separate video. But yeah, this is just in terms of like a simple state machine, this is your simple state machine. But yeah, thank you guys for tuning in.
Canon Controls is your gateway to mastering LabVIEW. Dive into programming for data acquisition, industrial communications, and manufacturing automation. Explore how to enhance your projects with cybersecurity best practices. Join the journey to elevate your skills and secure your systems with every episode.